Welcome back to the Pulse of Progress, the show where we break down the biggest breakthroughs in science and what they mean for you, the everyday listener. I'm your host, Alex Reed, and today we've got a real treat. Joining me is Dr. Elena Vasquez, one of the world's leading minds in materials science and climate innovation. Dr. Vasquez, thanks for being here.
Thanks for having me, Alex. I'm excited to chat about something that could really shake up how we tackle climate change.
Oh, I love a good shake-up. So folks, today we're diving into a game changer out of Northwestern University. Researchers there have figured out a way to pull carbon dioxide, yep, that pesky CO2 we're all trying to get rid of, straight out of the air using affordable, everyday materials. Dr. Vasquez, let's start simple. What's the big deal here?
The big deal, Alex, is that we're talking about direct air capture, or DAC for short, which is like a vacuum cleaner for the atmosphere. It sucks up CO2 that's already out there, not just from smokestacks or factories, but from everywhere. The catch has always been that it's expensive and tricky to scale up. But this new research, it's showing us we can do it with materials that are cheap, abundant, and even sustainable. Like stuff we can pull from organic waste.
Wait, hold up. Organic waste? Are we talking like banana peels and coffee grounds here?
Laughs. Not quite banana peels, but you're not far off. Think more along the lines of feedstock or byproducts we can tweak into something useful. The team at Northwestern tested things like activated carbon, which you might find in water filters, and metal oxides like iron or aluminum oxide. These are materials we already have in bulk, and they're showing they can grab carbon dioxide just as well as the fancy, pricey stuff we've been using.
Okay, so we've got affordable materials acting like CO2 sponges. How does this actually work? I heard something about humidity being the secret sauce.
Exactly. This is what's called moistureswing capture. Picture this. When the air is dry, these materials snatch up carbon dioxide like a magnet. Then, when the air gets humid, say from natural weather changes or even a little engineering trick, they let it go. It's like a catch and release system. And the best part? It doesn't need a ton of energy to heat things up like older methods do. That's a huge cost saver.
So it's like the material's playing a game of hot potato with carbon dioxide, but humidity's the signal to pass it off. That's wild. Why hasn't this been done before?
Well, it's not that it hasn't been tried, it's just been stuck in a rut. Most DAC systems relied on these engineered polymers called ion exchange resins. They work great, but they're expensive and not exactly scalable for the whole planet. What's new here is the team said, hey, let's look at what's already out there. Cheap, plentiful stuff, and see if it can do the job. And it turns out it can.
I love that, using what's already around us. So what are these new materials? Give us the rundown.
Sure. They tested a bunch of options. Activated carbon stood out. It's super porous, like a sponge with tiny pockets where carbon dioxide can hide. Then there's nanostructured graphite and carbon nanotubes. Fancy names, but they're basically carbon arranged in clever ways. On the metal side, they used iron oxide, aluminum oxide, and manganese oxide. Aluminum oxide and activated carbon were the fastest at grabbing carbon dioxide, while iron oxide and nanostructured graphite could hold the most. It's like picking the right tool for the job.
Okay, I'm picturing these little nano sponges soaking up carbon. But here's the million-dollar question for our listeners. Why should they care? How does this actually help the planet?
Great question, Alex. Carbon dioxide in the atmosphere is the main driver of climate change. Think hotter summers, wilder storms, rising seas. We're pumping out more of it every year, especially from things like planes, farms, and concrete production, where cutting emissions is really tough. This tech lets us clean up that mess after it's in the air. If we can scale it up cheaply, it's like hitting an undo button on some of those emissions.
An undo button for climate change? Sign me up, but you said if we can scale it up. What's the holdup?
Scaling is the tricky part. Right now, this is lab-tested brilliance. We know it works on a small scale. The next step is pilot projects, real-world tests to see how these materials hold up over time, how much energy they really use, and how cost-effective they are at, say, a farm or an airport. The researchers also found that pore size, those little pockets I mentioned, matters a lot. Too small or too big, and it doesn't work as well. They're figuring out the Goldilocks zone, around 50 to 150 angstroms, to max out performance.
Angstroms? You're losing me with the sciencey units, Doc. Break it down for us regular folks.
Laughs. Fair enough. An angstrom is super tiny. Think a billionth of a meter. It's just a way to measure the size of those pores. The point is, they've cracked a code. Get the pore size just right, And these materials can trap way more CO2. It's like designing the perfect net to catch fish. Too big, they swim through. Too small, you can't catch enough.
Got it. Perfect net, perfect catch. So what's next? Are we years away from seeing this in action?
Not necessarily. The team's already calling for pilot studies. And since these materials are so accessible, it could move faster than traditional DAC. Imagine a future where farms or cities have these systems running quietly in the background, using natural humidity shifts, like day versus night, to clean the air. It's not sci-fi, it's just engineering we need to tweak and test.
I'm sold. Cleaner air, cheaper tech, and maybe a cooler planet. That's a win for all of us. Before we wrap up, any last thoughts for our listeners?
Just this, carbon capture's still young, but it's growing up fast. This research shows we don't need to reinvent the wheel. Just use what's around us smarter. It's a reminder that science can find answers in unexpected places, and that's hope worth holding on to.
Hope worth holding on to. Love that. Dr. Elena Vasquez, world-class scientist and optimist. Thanks for breaking this down for us. Folks, if you want to learn more, check out the paper in Environmental Science and Technology. We'll link it in the show notes. Until next time, keep curious and we'll keep bringing you the pulse of progress.